Alright, hello! Welcome back. This is everything you need to know about JPEG, episode 9. Today we are learning about progressive JPEGs. We've already talked a bit about what makes a progressive JPEG special, but let's start from the beginning. What is a progressive JPEG? To answer that, let's do a very quick recap of a baseline JPEG. I trust that you've watched all the episodes up to now, so you should already know that a baseline JPEG involves two main steps. Step 1 is reading the frame header or start of frame marker, as well as table definitions like quantization tables and Huffman tables, as well as a couple other more minor things like the restart interval definition and so on. And that's step 1. And then step 2 is reading the scan header or start of scan marker, followed by the Huffman coded bit stream, which the specification calls entropy coded segment or ECS. And that's all there is to it. And as we know by now, this scan contains all the DCT information for every block in the entire image. So in a progressive JPEG, there will be many scan headers and entropy-coded segments, each of which will pass through the entire image. But with each new scan, you get a little bit more detail. So now the JPEG file will contain a whole bunch of scans. But also, between scans, there can be a couple different kinds of markers. Most importantly, new Huffman tables, and also new restart intervals. So this is going to be kind of a paradigm shift from what we're used to. Usually, when we've gotten to the entropy-coded segment, we're kind of done parsing markers, other than the restart markers that are in the entropy-coded segment and the end-of-image marker. But those are the simplest kinds of markers anyway. There were at least no more markers that had actual data, like the start of frame, tables, start of scan, and so on. But now we're going to be constantly needing to go back and forth between parsing markers and parsing Huffman coded bit streams, all the way until we get to the end of the last scan. So that's going to mean kind of a change in how we parse the input file in our decoder, but we'll get to that when we get back to our code. For now, what we need to talk about is why are there so many scans, how does the information provided in each scan differ from one another, and how do we parse a progressive entropy-coded segment? Well, first let's talk about why the idea of a progressive JPEG was thought up at all. The best scenario for understanding this is imagine a computer with a browser visiting a web page, trying to view JPEG images on that web page over a very slow internet connection. Just knowing what we know already about baseline JPEGs, if we ignore progressive for a moment, the browser kind of has two choices about how it can handle an image that's loading so slowly. The browser could just wait ages for the entire file to be received and then decode the whole image at once in one go and then present the final result to the user. That is slow and awful and boring. The other thing the browser could do, let's say this is our image, and let's say it'll take a whole 10 seconds for your computer to download the entire file. What your browser could do is, after a couple of seconds, after it's received this much of the Huffman coded bit stream, which we know because it's a baseline JPEG, the information goes from left to right, top to bottom. The browser could perform the rest of decoding, by that I mean dequantization, inverse DCT, and color conversion, on just this much data, and show that in the web page. Then after a few more seconds have passed, maybe it has this much of the bit stream. Then it performs all of decoding all over again. And basically this repeats until the last bit of the file has been received, and it performs decoding one last time. You may have even seen this yourself sometimes when a page is loading, and over the course of several seconds, a page kind of slowly grows from top to bottom. So the purpose of the progressive JPEG is to improve the user experience when the network transmission is the bottleneck. In the end, the image is going to look the same, but if the most important information is put in the first couple of scans, and each scan does give you information about every block in the image, then after just a little bit of time has passed and you've only received the first scan, you can actually see the whole image. Obviously, the quality won't be great, but there will be something to show over the entire surface area of the image. Then as you get the rest of the scans, each block will become a little bit more refined until it looks as good as it can. So for a progressive JPEG, I'm not going to try drawing it perfectly because I'm a terrible artist. But after just the first scan, you'll have information about the whole image, and it'll be very blocky, so you'll know generally what color the last block is supposed to be. And then the next scan will give you a little bit more information, and then the next couple of scans will give you even more detail. So how is the data broken up between scans? There are two different mechanisms, and we've mentioned both of them before. One of them is spectral selection, and the other is successive approximation. So how does spectral selection work? You may remember from episode 2 that the start of scan header gives us two variables called start of selection and end of selection. And you may remember that for baseline JPEGs, these must have the values 0 and 63. That already kind of gives away what they're for. These values mean that for the upcoming scan, the Huffman coded bitstream will include information on the DCT coefficients starting at this index up to the end index, which is inclusive. And like usual, these indices refer to the zigzag path. So each of their values must be between 0 and 63, and then you have kind of the obvious constraints that the start value should not be larger than the end value, but they can be equal, meaning the scan only includes information on a single coefficient in each block. And then in addition to that, there are two more caveats that are important to know. One is that in a progressive JPEG, each scan must not mix DC and AC coefficients. Each scan should be only DC, in which case the start and end will both be equal to 0, or the scan will be AC only, meaning start is something greater than 0, and then of course end is also greater than 0. And the second is that for an AC scan, there must only be one color channel present in the scan. You may recall way back from episode 2 that the start of scan marker tells us the number of components that are present in the scan, but we've not really worried about this too much because it has always been equal to the number of components that are present in the start of frame marker. But now this number can be different. More specifically, it must be 1 if the scan is an AC scan. For DC scans, it can be 1 or 3. That actually leads to one other kind of oddity that is good to know, and that has to do with how progressive JPEGs interact with chroma subsampling. You may recall from the episode on chroma subsampling that in the case of both horizontal and vertical subsampling, for each MCU, we read 4 luminance blocks in a row before we read 1 blue chrominance and 1 red chrominance block. Then these 4 luminance blocks get placed in a 2x2 grid for the current row of blocks as well as for the next row of blocks down. However, what might be a little bit unexpected is if there's a scan that only contains the luminance component, subsampling is kind of ignored or reevaluated. What I mean by that is, for each scan, subsampling is really only evaluated between the components that are even involved in the scan. So if there's only luminance, there isn't a need to do this whole 2x2 grid nonsense. So a progressive scan that only contains luminance, even if it's in a chroma subsampled image, will just go straight left to right down the row and then move on to the next row when it's time. But for any scan that does mix all the components, the ordering of the subsampling will work the same way as before. So spectral selection isn't that complicated. Now let's talk about successive approximation. Just like with spectral selection, this is controlled by two variables that we read out of the start of scan header. They're kind of unhelpfully named successive approximation high and successive approximation low. I'm just going to start calling them SA high and SA low. The important one is actually SA low. This tells you, when you read a whole new coefficient out of the Huffman coded bit stream, how many bits should you shift that value to the left before storing it. Remember what a progressive scan does. It gives you the most important information first and then all the picky details later. So that means the first couple scans are going to have approximations. They're going to be stored in the bit stream as kind of small numbers, and then we're going to bit shift them to the left to turn them into bigger numbers that have nothing but zeros in their lower bits. That's the approximation part. SA low tells you how many bits to shift. Then all those bits that are still 0, they're going to be filled in by the later scans. So if SA low is the number of bits to left shift, what is SA high? Well, the value of SA high will be the previous SA low value for the last scan that covered the same coefficients for the same color channel. That doesn't necessarily mean the previous scan, because the previous scan might have covered a different spectral selection, or it might have covered different color channels. But the previous scan that covered the exact same coefficients of the same color channel as this scan, whatever its SA low value was, will be the value of SA high now. Now for the very first scan, or for any scan that visits some coefficients for the very first time, the value of SA high will simply be 0. The purpose of this really is so that the current scan knows exactly how to pick up where it left off without actually needing to have some kind of lookup information about all previous scans. But as far as understanding the upcoming Huffman-coded bit stream, the value of SA low is much more important. So now that we know not only do we visit every block more than once due to spectral selection, we also potentially visit each coefficient many times due to successive approximation. We already know that even in baseline JPEGs, there's a difference between DC and AC coefficients, and they get treated differently and read differently out of the Huffman-coded bit stream. So of course, the same is going to be true here. There's also a big difference in how each coefficient is treated if it's the first visit versus how it gets treated if it's any subsequent visit to those coefficients, which we call refinement. So we're going to need 4 different procedures for handling coefficients in the Huffman-coded bit stream: a DC first visit and an AC first visit, a DC refinement, and an AC refinement. The good news is that the first visit decoding is actually very similar to baseline decoding, with the only major difference being that left shifting that I mentioned based on the value of SA low. There is one other extra rule that has to do with AC first visit, and that's kind of a new way to skip entire blocks of all zeros. It is kind of similar to special symbol 00 that we're already familiar with, but on a bigger scale. We know that special symbol 00 means that we're done with this block and the remaining coefficients are all 0. That is still going to be true here, but now we also have 14 new symbols, called the end of band symbols. The stretch of the zigzag path covered by the start and end of selection is called the band. So what are the values of the 14 new symbols? Well, we know that the bottom nibble of the symbol, the length of the coefficient, must not be 0, unless we're talking about special symbol F0 or special symbol 00. The 14 new symbols are all the other possible values where the length of the coefficient is 0, so where the high nibble is 1 through E, or 1 through 14. These end of band symbols mean not only are we done with the current block, but we're also going to skip potentially a large number of the next blocks because those are all 0 as well, at least for the bands that are part of this scan. And we use the value of the end of band symbol, whether it's 10, 20, 30, and so on. We use its value to know exactly how many of the next blocks are going to be skipped. Now, right before we actually talk about how to figure out that exact number, I'll just mention that we know the maximum number of symbols that should appear in a Huffman table is 162, these 162, and now we're basically adding 14 more onto that. So now the maximum number of symbols allowed in a table is 176, although in my experience I've never ran into a Progressive JPEG file that actually uses more than 162 or uses all 176. That is because every Progressive JPEG file that I've encountered has Huffman tables that are optimized, where the symbols that didn't need to be used by the scans were just omitted from the tables entirely. But I suppose it's possible that a file may contain up to 176, so we should allow it even though I'm not quite sure how common it is. Returning to our current slides here, let's figure out how to deal with that end of band symbol. All we need to really focus on is that number 1 through 14, and let's call that number n. We start by saying the number of blocks that we're going to skip is 2 to the power of n, but of course it's not really likely that the exact number of blocks that need skipping is 2 to the n exactly. But we can get any number between 2 to the power n and the next power of 2, 2 to the power of n plus 1, by just reading the next n bits from the stream. So for example, if n was 3, 2 to the power of n is 8, and 8 in binary is 1, 0, 0, 0. And because n is 3, we'll read the next 3 bits, so basically we'll fill those in. Whatever this number ends up being, that's how many bands we skip until we begin reading coefficients again. Other than that, decoding the first visit of an AC coefficient is the exact same as baseline. Next, DC refinement is very simple, and it doesn't even have anything to do with Huffman tables. For refinement, both DC and AC refinement, we only read one new bit at a time for each coefficient. And for DC refinement specifically, it really is quite that simple. For each DC coefficient, we read a single bit, we shift it to the left by the value of SA low, and we join that new bit onto the DC coefficient that we are refining. So very, very simple. And then lastly, AC refinement. This one is the monster. So what makes AC refinement so complicated? It still revolves around the idea of using Huffman decoding to extract symbols and using the symbol to know how many zeros to skip, but what it means to skip zeros is kind of more complicated. So we read a symbol and we learn how many zeros we need to skip, and we learn the length of the next coefficient. But we know that this is a refinement scan, so we know that some of the coefficients already have partial values in them. For the coefficients that are still equal to 0 at this point, there's two reasons they might be equal to 0. Number one is that it's truly 0 and always will be, even after we've read every scan. The other reason is maybe it's 0 so far because the only bits of that coefficient that are non-zero are going to come in future scans. Because this is a refinement scan, we know we're only going to be reading one new bit at a time for every coefficient, so length should actually be 0 or 1. We're either reading a new bit or we're not. We also talked about how those end-of-band symbols apply whenever length is equal to 0, and that's still going to be true here, and we'll talk about that more in a moment. But when length is equal to 1, then this still represents the number of zeros to skip, pretty similarly to how it did with baseline decoding. The big difference, though, is that this value only counts the coefficients that are still 0. What I mean by that is the blocks we're going over, because this is a refinement scan, are going to be filled with partial coefficients that have non-zero values. If the number of zeros we're supposed to skip is, say, 5, we might actually advance by more than 5 coefficients because we keep going and count how many are actually 0. And if we reach a coefficient that's non-zero because of a past scan, that does not count towards the number of zeros we're skipping. On top of that, for those coefficients that are non-zero, that don't qualify as getting skipped, we actually read a new bit for them, regardless. And that's without using the Huffman tables. So let's say the number of zeros to skip equals 2, and the length equals 1. And let's say here are 5 sequential coefficients that we have so far in our block along the zigzag path. And these are 5 coefficients that belong to the current spectral band. And our for loop, our variable, is currently pointing at this position, which already has a non-zero value from some previous scans. We need to skip 2 zeros, but starting here, this isn't 0, so it doesn't count as one of the 2, and we have to read a bit for it. That new bit might be 1 or it might be 0, doesn't matter, but this I'm using to denote is appending a new bit to this non-zero coefficient. Then we move on, and we encounter a coefficient that's still equal to 0 in our block, so we skip it, and that's one of our 2 skips. Then the next coefficient is non-zero, so we read a bit. Then we encounter another 0 coefficient, so that is the second of our 2 skips, and we move on. Now, because we've accounted for all of our skips, this coefficient ought to be 0, and we read a bit for it. And the reason that this value was still 0 up to now, even though this is not the first scan, it's a refinement scan, is just because on the first visit, all the higher, most significant bits of this coefficient happened to be 0. It wasn't until a refinement scan, where we're focusing on the lower bits, did this coefficient finally get a non-zero bit. Oh, and this bit for this new coefficient that relates to this symbol, the bit actually gets read right after the symbol. Then you handle all the zeros and the new bits, and then you place the bit that you read at the beginning. Then after you place this new bit in the coefficient, as long as you're not done with a spectral band, then you go back to the beginning of the process and continue on along the band. Now all of that I just described only applies when length is equal to 1 or for special symbol F0. If length is 1, then you handle the number of zeros to skip, which might be 0 by the way, and then because length is 1, you place that bit. Or if this is about special symbol F0, then you skip 15 zeros, and length was 0, so you skip 1 more as well, so essentially you skip 16 positions. But you still read bits for the non-zero coefficients along the way. So then what's left to talk about is when length is 0, other than special symbol F0, so when the number of zeros to skip is between 0 and 14. Those end-of-band symbols are pretty similar to how we handle end-of-band symbols during AC first visit scans. That value of n from 0 to 14 gives us kind of the base power of 2, 2 to the n, skips, plus we read n more bits, and that gives us our total number of skips. However, with AC first visit, if our number of skips is still positive, then we just decrement that variable and return because there's nothing to do for that block. For AC refinement, we still have to process the non-zero coefficients in the exact same way as this type of skipping. If we're supposed to skip so many blocks because of an end of band symbol, we can't just skip the whole block. We pass through it, and for every non-zero coefficient, we read one more bit. But importantly, we don't read any symbols. There's no Huffman decoding going on when we are skipping a band. Lastly, before we move on to implementation, let's get a better idea of what a whole sequence of scans looks like in a real JPEG file. There are really two categories of progressive JPEGs that we really care about. One is a progressive JPEG that only uses spectral selection. That is to say, the SA high and SA low are always equal to 0 for every scan. It doesn't use successive approximation, and therefore every scan is a first visit scan. And the second category is a progressive JPEG that does use successive approximation. And that's also called a full progression. So first, let's look at a sequence of scans that you might find in a progressive JPEG that does not use successive approximation. Let's use this MCU block over here to illustrate which coefficients we've already read in the scan so far and which ones are left to read. Scan number 1 might have a spectral selection start of 0 and a spectral selection end of 0, which would make this a DC scan, and it might have all three color components. Because in this example there is no successive approximation, we know that we'll read the entirety of every coefficient. In other words, there will be no refinement. So for this scan, starting at index 0 and ending at index 0, we'll get the coefficient data for Y, CB, and CR. So basically what that means is after the first scan, we have the entirety of all three color channels of every DC coefficient in every block. But we have no information on any of the AC coefficients. And moving on to the second scan, the start of selection is 1 and the end of selection is 5, meaning this is an AC only scan. And AC scans are only allowed to have one color component, in this case, CB. And along the zigzag path, positions 1 through 5 are 1, 2, 3, 4, and 5. So after scan number 2, these are the coefficients that we have. For the third scan, the spectral selection is the same, but for this time, it is only for the CR component. So our coefficients will look like this. For scan number 4, again, the same spectral selection, but this time for the luminance channel. After that, our coefficients look like this. Then scan number 5 will have all the rest of the coefficients for the CB channel from 6 through 63. Then our coefficient data would look like this. Then continuing with that pattern, scan number 6 gives us the rest of the coefficients for the red chrominance channel. At that point, our coefficient data will look like this. And for the very last scan, we get the remainder of the coefficients for the luminance channel. Then at this point, we finally have all the DCT coefficient data, and we can move on to dequantizing, performing inverse DCT, and performing the color conversion, and we could look at the final perfect image. If we were to stop after a particular scan and not finish the rest, and then move on to decoding, we'll get a decent looking image, but it will just be missing whatever detail was skipped by skipping those scans. Now, what about a JPEG that also uses successive approximation? This time there are 10 scans, so the information is going to get a little bit dense on screen, but I think it's useful to see the whole example all the way through. The start of selection and end of selection are 0, so it's a DC only scan. Because it's a first visit, SA high is 0. And SA low is 1, meaning there will be 1 bit left on these coefficients after the scan is done. And this scan includes Y, CB, and CR. So we have the Y, CB, and CR DC coefficients, and this missing strip here is how I'm signaling the fact that we have 1 bit left. Scan number 2 goes from index 1 to 5. SA high is 0 because it's a first visit on these coefficients. SA low is 2, meaning we'll have 2 bits of precision left for future scans, and this scan is just luminance. So that will look like that, and of course this wider gap is to indicate we have 2 bits left. Scan number 3 goes from index 1 to 63 of the red chrominance channel. It is a first visit, and there will be 1 bit left after the scan is done. Now our coefficient data will look like this. Every single red chrominance coefficient is missing 1 bit of precision at this point. For scan number 4, it's exactly the same as scan number 3, except for the blue chrominance channel. Now our chrominance data looks like this. Then on scan number 5, back to the luminance channel, getting the rest of the coefficients on their first visit, with 2 bits left remaining. Then our coefficient data will look like this. Now, on scan number 6, this is finally the first time we are revisiting or refining coefficients. So SA high is 2. That is simply what SA low was the last time that these coefficients were visited, which if you look at it refers both to scan number 5 and scan number 2. Those two scans together covered from 1 through 63 of the luminance channel, and SA low was 2. And now SA low is 1, so we're still, after this scan, going to have one more bit left on all these coefficients on the luminance channel. So after scan number 6, our coefficient data looks like this, just one bit left on every coefficient. Scan number 7 is finally another DC scan, so from 0 to 0. The old SA low was 1 all the way back here, so SA high is 1. And after this, we'll be done with the DC coefficients. There will be no bits left, so SA low is 0. And this DC scan has Y, CB, and CR. All that happens in this scan is these coefficients are finished. So that is what our coefficient data looks like now. For scan number 8, we go through all 63 AC coefficients, getting the remaining bit, so SA low will now be 0 for the red chrominance channel. So now we have all the red chrominance data. Scan number 9 is exactly the same, but for blue chrominance. So now we have all the CB data, and for the very last scan, of course, we get the last bit for all the luminance coefficients. So you can see you're always going to get all the coefficient data, whether it uses a successive approximation or not, or whether it's baseline or progressive. You're always going to get all the data. The only thing that matters is what does the image look like at those intermediate stages between scans. Now that we have a really strong grasp on the procedure, let's go back to our code and implement the decoding of progressive JPEGs. So we are going to start off with the same code from the end of last episode, but with some minor refactoring and cleanup. So real quick, let's go over that. Last episode, we talked about how we had this struct named MCU, and that was fine for a while, but the name just didn't make sense anymore once we started handling subsampling, and block would be a better name. So I've went ahead and renamed it to block and changed all the references in the other CPP file as well as all the comments. I'm not going to go over all the refactoring line by line because that's not really necessary, and none of the changes will throw you off really, but yeah, I renamed the MCU struct to block. Similarly, this struct used to be called header, which we mentioned is not a very sensible name because it's not just the header of the JPEG image, it's really all the JPEG image data because we're storing all the image data in this vector of bytes. So I changed it to a more appropriate name, JPEG image, and again changed all the comments in the CPP file. Moving on to a more important change, in our color component struct, we used to have a Boolean flag called used to indicate whether or not the image uses a particular component or not. But now we're having two separate flags, used in frame and used in scan. This distinction didn't matter before because for baseline JPEGs, if it's in the frame, it's also going to be in the scan. But now, of course, the distinction does matter because each scan may or may not have all the same colors that are in the frame. Going back to our JPEG image struct, I've added a new variable here called components in scan. This is a value we read during the start of scan marker. And again, its value didn't matter because for baseline JPEGs, it should always match the value of num components, which we already have in this struct. But now for progressive JPEGs, the value of components in scan might not be equal anymore. So we want to hold on to that value permanently. And lastly, our pointer to our block array, which used to be the MCU array, is now in the JPEG image struct directly. What we used to be doing almost all the time is just pass both the JPEG image struct and a block pointer to each function call. So it makes more sense to just put the pointer in the image struct, then you only need to pass the image struct. Over in the CPP file, other than the renaming of those two structs, there's also some improved error handling, but I'm not really going to go through all that. We can see now while reading a start of frame marker, when we handle a color component, we are now setting used in frame to true. Other than that, no changes to reading the start of frame. Likewise, when reading a start of scan, at each new scan, we're now setting used in scan to false for every color component, and when we handle another color component, we set used in scan to true. Also, when the scan tells us how many color components are in the scan, we're now storing that in that new variable in the image. Next thing to point out, I've moved the generate codes function towards the top so that we can generate the codes as soon as we read each individual Huffman table. Instead, what we were doing before is calling generate codes on every table at the start of Huffman decoding. That was fine when there's just one scan, but that would be redundant if we did that for every table for every scan. So now we're just generating the codes each time we read a table. Okay, next. The way that we've been reading baseline JPEGs is with two marker loops that go back to back. The first marker loop is for reading the frame header, quantization tables, and so on, and the second marker loop is for the one and only baseline scan. And those two loops were back to back in the same function, but I've broken them up into two separate functions now. The first function is read frame header, but the logic is the same. Then this returns once it hits the start of scan marker. And then the second is read scans. Again, the logic is the same, but it handles the baseline scan data. All that logic used to be in this read JPEG function. So this function still exists, but all the logic has been moved out into those two helper functions, and read JPEG itself is really short. And its real job is about memory allocation and error checking. All it really does is it calls read frame header, and if that's successful, it calls read scans and then returns the result. This new structure is just going to be really handy for how we're going to need to modify read scans for handling progressive JPEGs. And lastly, I really improved the speed of our bitmap file output. Here in write bitmap, we are now allocating a buffer right at the start based on the size of the bitmap file, and then we're placing bytes into that buffer and keeping track of our position in the buffer with this buffer pause variable, instead of having outfile.write on each of these lines. Of course, a similar change was made to our helper functions here, putShort and putInt. Then at the very end of this function, we write the entire size of the buffer to the output file and then close the output file. Doing a single .write of the entire buffer is much, much, much faster than doing thousands of .writes with a single byte at a time. Okay, all the other changes I've made are very small and not worth going over individually. Okay, now returning to progressive JPEGs, where do we start? Well, I mentioned the paradigm shift of how we handle the input file because of this need to go back and forth between reading marker data and reading bits at a time for a scan. What we do now is we use a file stream to process all the markers. Then once we get to the scan, we take all the scan data, put it into a byte vector, close the file, and then we only worry about the byte vector. Now we're just going to stop using the byte vector altogether, and we're just going to use the actual file stream the whole time. What that really means is we're going to need to change the bitreader class to deal with file streams instead of byte vectors. So let's do that. So we will replace the byte vector with a file stream. We will replace the constructor with a constructor that takes a file name string and uses that to open the file. For completeness, we'll add a destructor that will close the file once the bitreader goes out of scope. You may remember that in our marker reading loop, we have used not_in_file, !in_file, to detect if the file still has more bits in it. But because we're using the bitreader as a wrapper to the file, we want the bitreader to be able to tell us if it still has bits, which we are inverting the logic here, so we need not_in_file. Of course, we need to fix the read bit function, but we're also going to want to add a read byte function for the marker handling. And we might as well add a read word function as well, basically reading a 2-byte value. This is the exact expression we use all over the place in our marker handling. Now, in order to fix the read bit function, we're actually going to change the meaning of this next byte variable. Next byte used to be an index into the position in the vector for the byte that we're reading. But now this index position is not really useful. So we're going to start using next byte as the actual byte value coming from the file. So the most important thing is if next byte is the byte from the file, we use the value of next bit, same as before, to get that bit. We also want to increment next bit so that the next time this is called, we read the next bit from the byte, and then we return the bit. If next bit equals 0, we're about to read a bit from a brand new byte, so we need to fetch that byte. If the file has no more bytes, we're done. Otherwise, we get a new byte from the file. Another thing to point out here is that when we were using the byte vector, we kind of pre-processed that stream of bytes in the sense that we removed all the RST markers and so on. Because we're reading straight from the file right now, it's not pre-processed, so we will encounter those RST markers. Same as before though, we just want to skip them and then get the next byte after that. So we watch for FF values coming from the file, and we want to peek at the next byte in the file. By calling peek, we will get the next byte without actually advancing our position in the file. Like usual, if the file contains many FFs in a row, we just kind of ignore that. Doesn't usually happen. If this byte that we're peeking at is 00, 0, that means we want to return the literal FF as a raw byte. So this infile.get is a way of ignoring the 00, 0, and then we break from this while loop so that we return down here using the FF that is still stored in next byte. If the marker value we're peeking at is not 00, 0, maybe it's a restart marker, and if so, we ignore it, and we overwrite next byte with whatever the next byte is after the restart marker. Otherwise, we must be looking at some invalid marker that should not be appearing in a Huffman-coded bit stream. The read bits function doesn't need any changes at all, and the align function is now going to be a lot simpler. When we need to align at the start of a new restart interval, we just set next bit to 0. Then the next time read bit is called, because this is 0, we'll do the fetching of the next byte. So that is the new bit reader class. Now we need to start using it correctly. Currently, we declare the bit reader when we begin Huffman decoding, but obviously we want to declare it much, much sooner now. So we can delete it from here, and we'll come back to refactoring this function later. Now we want to declare the bit reader at the start of read JPEG, where we're currently opening the input file, which we are not going to do on our own anymore. That's, of course, going to be handled by the bit reader. So we declare the bit reader using the file name string. Now, every time we get a red squiggle here, we just change it to the bit reader equivalent. So instead of asking if the file is open, we ask if the bit reader has bits. We don't need to explicitly close the file anymore. And now everywhere that we pass the in file, we're now going to be passing the bit reader. That's all we need to do to read JPEG for now. Now all these functions above that take the in file, we're going to change it to take a bit reader. And for example, if I just look at one of these, every time we do infile.get by itself or infile.get twice to read a 2-byte value, we'll replace that with the bit readers getByte and getWord. So let me just go and make all those changes and come back. So there we go. Now all our marker reading functions are using the bit reader as they should. Now if we go right back to decoding Huffman data like we were talking about, we need to refactor this slightly. Basically, because this function created the bit reader itself, it now no longer has one at all. So we'll just pass it in as a new argument. And the place we call this function is actually in main, in our main sequence of events here. But let's take it out of here and put the Huffman decoding in read JPEG, because really that's the only way to handle multiple scans back to back. We do the Huffman decoding while reading the JPEG. So we'll simply delete this, and we'll put it back right after reading the start of scan marker, which that would be right here after reading start of scan. But actually, let's take both of these lines out so that we can just break, once we detect the SOS marker, break from the read frame header function, so that in read JPEG, this will return and we'll move on and read scans, and then we'll process the start of scan marker and all the Huffman data. This read scans function needs a lot of work anyway because it's still trying to use the byte vector. So for now, we can really get rid of this old way of handling the scan. And all we'll do for now is read the start of scan marker and decode the Huffman data using the bit reader. Now we've finally gotten rid of all the code that used the byte vector, so let's get rid of that from our struct. And we can get rid of our include for that as well. Now back in the CPP file, the only error we're going to get is because we used to print the size of the scan. Let's just not do that anymore. And if you think about it, this isn't a very helpful way of printing information about the image anymore either. Right now, our print header function prints quantization tables, start of frame, Huffman tables, AC and DC, and start of scan information. And all of this gets printed in main after we read the whole JPEG file. So that scan data will really only relate to the last scan. What we can do instead is let's replace the print header function with two separate functions, one for printing the frame information and one for printing scan information. So let's just replace the old print header function with print frame info, which prints the frame information and the quantization tables, and print scan info, which prints the scan information and the Huffman tables, because the Huffman tables are allowed to change between scans, and the restart interval, which is also allowed to change between scans. Now let's simply call print frame info in read JPEG after we successfully read the frame header, which is right here. And then we can print the scan info right after reading the start of scan marker, which is right here. Now at this point, after reading the Huffman coded bit stream, in a baseline JPEG that we've been dealing with so far, we should expect the end of image marker and then the end of the file. At the bottom here in main, we no longer need to print the header after reading the entire JPEG file. Now that we've changed a whole lot, let's make sure that this approach of reading the Huffman coded bit stream using the bit reader still works for baseline JPEGs. Before we do that, we do need to forward declare this decode Huffman data function because now we're using it much earlier in our program. So here are our three main test files, cat, gorilla, and turtle. I put them into a tests folder just for organization. If we make, and then we process those three tests, you can see all our refactoring didn't break anything. We can still handle those baseline JPEGs just fine. If we really want to be sure, we can test on our subsampled JPEGs as well. And no problems there. Now that we finally got all the refactoring out of the way, most of the rest of the work that we need to do has to do with fixing the read scans function to actually read all progressive scans, and fix the decode block component function so it can handle DC first visits and refinements and AC first visits and refinements. Before we do that, one last change with reading the frame header, and that is simply that now we allow SOF2, which is the marker for progressive JPEGs. Now let's focus on progressive scans. So in decode block component, all this code is still good, but it only relates to baseline JPEGs. So basically, let's wrap all of this. So that it only applies when the frame type is SOF0. Of course, that means we need to pass the image to this function now. So we'll add that as a new argument, and I'll kind of clean up this list a little bit more anyway. But the important part is we're now passing in the image. Of course, that means in the decode Huffman data function where we call this function, we need to pass the image here. So we will do that. While we're here, you might notice that this for loop goes through every component in the image, but of course, not every component is necessarily part of the scan. So before trying to decode the block, we will check that this component is in fact part of the scan. Now going back to the actual Huffman decoding, we know this SOF0 code is okay, but here we want to handle SOF2. And here we want to determine if this is a DC first visit, a DC refinement, an AC first visit, or an AC refinement. First, we tell if this is a DC or an AC scan by looking at the value of start of selection. If it's 0, it's a DC scan. If it's not 0, it's an AC scan. And we determine if this is a first visit or a refinement scan by looking at the value of SA high. If SA high is 0, it's a first visit. If it's not 0, it must be a refinement because it reflects the old value of SA low on the previous scan. For now, let's not worry too much about the refinement scans because as we saw, it's not always required. You might have a progressive JPEG that doesn't use refinement or successive approximation at all. So let's just focus on the first visit. We know the DC first visit is pretty similar to the DC coefficient of baseline JPEG, so let's start with that. The only real difference is we have to use the value of SA low to know how many bits to left shift this new coefficient by before storing it. And then it's important to know that for the previous DC value that we need to know, we make a copy before doing the left shifting. Now, for the first visit of an AC coefficient, again, we can kind of start with almost a copy of baseline AC decoding. Except instead of starting I at 1 and going to 63, we use the start of selection and end of selection variables for the spectral band for this scan. Other than that, it's pretty similar. We get the next symbol. We split that up into the number of zeros and the length of the coefficient. If the length of the coefficient is non-zero, we skip based on the number of zeros. Read that coefficient, store that coefficient into the component, and again we left shift based on the value of SA low. If the coefficient length was 0, then we'll be here. If the number of zeros is 15, that is special symbol F0, so we handle that accordingly. Otherwise, this must be one of those end of band symbols. So in order to handle this, we need a new variable. The function that we're in right now only deals with a single block, but this end of band skip variable is going to extend across blocks. So we will declare this variable in the decode Huffman data function. It's going to be kind of similar to this previous DC's array. We declare our number of skips. This end of band skip variable also gets reset to 0 whenever we hit the end of a restart interval. And we need to pass this variable to the decode block component function. So then we'll add that argument up top. And now when we encounter an end of band symbol right here, remember we start by saying the number of blocks that we're going to skip is 2 to the power of n, where in this case n is num zeros between 0 and 14. And we can just subtract 1 right away. That's kind of accounting for this current block. Additionally, we need to read n more bits, so that's done here, and that's how many more skips in addition to the power of 2 number of skips. And the only reason we're putting this in its own variable is so that we can do our error checking for our bit reader. But assuming that worked, we just add the number of skips to the total number of skips, and then we break because we are done with the for loop that we're in here for handling this block. The only thing left is if we're starting this block for this AC first visit scan, we actually need to check that skips variable first, and if it's positive, we decrement it and we return. There's nothing to do for this block. There's no Huffman decoding to do. We're in the middle of an end of band run. We're almost ready to start testing this, but we just need to update our validation that we do when we read some of the markers. So if we go back to reading the start of scan, we now need to allow for these progressive spectral selection values. So if we go down to the bottom, here's where we are validating those values. Right now we're saying that the start of selection and end of selection must be 0 and 63. And let's also go ahead and fix our validation of the SA values, even though we're not too worried about those just yet. For baseline, we're saying that the SA high and SA low must both be 0. But now this only applies to SOF 0 or baseline JPEGs. And for progressive JPEGs, these are the rules we're going to be enforcing now. The start of selection must not be greater than the end of selection. The end of selection must not be greater than 63. If the start of selection is 0 and the end of selection is not 0, that's a problem because that means the scan is mixing DC and AC values. If the start of selection is not 0, meaning it begins at an AC value, but the number of components in the scan is not 1, that is a problem because AC scans should not contain more than one color component. And lastly, for successive approximation, if SA high is not 0, in other words, if this is a refinement scan, then SA low ought to be just 1 smaller than SA high. And that is because refinement scans should include just 1 bit. So if SA low is not SA high minus 1, then that is a problem. Okay, now that we have fixed all the validation of progressive values, and our read scans function will decode the first scan and then return, that means we're skipping all scans other than the first one, and we're not validating the end of image marker, but we will be returning from the read JPEG function, and then proceeding with the rest of decoding, dequantization, inverse DCT, color conversion, and finally bitmap output. So in our test files, let's make a new file called prog for progressive JPEGs, and in here we have parrot.jpg. This is the example file I used to illustrate in our slides the sequence of progressive scans for a progressive JPEG that does not use successive approximation. Let's see how our decoder handles this file now. Well, we certainly got a valid bitmap file. To understand the data that we got, we should look at our log here. If we scroll up past the Huffman tables, we see the start of scan information. Start and end are 0, so this was a DC-only scan. No successive approximation, so we got the whole coefficient with no missing bits. And we got information on all 3 color channels. So because this was a DC-only scan, every 8x8 block is a solid color. There's no chance of any variation within an 8x8 block because there were no AC coefficients at all. But we did get the average intensity of all 3 color channels. aka the DC coefficient. So now, how do we move on to the next scan? Oops, actually, I made a goof. You might be able to tell in this image that the brights are very bright and the darks are very dark. It's kind of subtle, but you can tell. Turns out here, when we handle the SA low value on the DC first visit, I kind of messed up my paste here and forgot to delete these old lines. Now if we do that again, that's much better. Still just as blocky, but now the colors are really the right average. Just for fun, let's add a couple more tests. Now we have a crab, the earth, a frog, and a panda. And let's run this again. And there we go, they all worked. We can see the blocky crab compared to the original, the blocky earth compared to the original, the blocky frog and the original, and the blocky panda and the original. Okay, next order of business is fixing read scans so that we don't just quit after the first scan, but we go all the way to the end of the file. These 3 lines are still good, we still need to do them, but now we need a new marker reading loop where we will process markers, like I said before, most importantly, new Huffman tables and new restart intervals, and new start of scans. So we start by reading 2 bytes. This is going to be structured pretty similarly to our marker loop from read frame header. We enter our while loop where we go for as long as the file is still valid, and once we reach the end of image marker, we'll break manually. Just like before, we always check if the file still has bits. Also, just like before, we produce an error if we are not actually looking at a marker right now. Our important exit condition is if the marker we're looking at is end of image. We also allow new Huffman table definitions, but only if the frame type is progressive. That's because this loop is still technically going to be used by baseline JPEGs, except the expectation is that the only thing a baseline JPEG will see is the end of image marker. Besides a Huffman table, we might encounter a new scan. These 3 lines are basically a repeat of the 3 lines at the top. We read the start of scan marker itself, we print the scan information, and then we do the Huffman decoding. Again, that only applies when the frame type is progressive. Next, we could have a new restart interval. Very easily, we just read the restart interval marker, again, only if the frame type is progressive. We're also going to need a check if the marker we're looking at is a restart marker. Now, these are only supposed to appear in the middle of the Huffman coded bit stream, but it's possible that the reason we are seeing one is because of this decode Huffman data call. It returns once it gets all the data it needs for the scan, but that might be right before noticing the very last restart marker. So we'll acknowledge it here, but there's nothing to do for it. Like we always do, we'll ignore multiple FFs in a row. But other than that, there aren't any other kinds of markers we should be seeing at this time, so we will report everything else as an error. And then before we go back up to the top of this while loop, we read the next 2 bytes to start parsing the next marker. So now that we've kind of restructured everything in advance, this was really easy to do nice and clean. Now let's see how far we get in our progressive test files. Just to make sure we know what we're looking at, I'm going to go ahead and delete all of our bitmaps from before and rerun it. And you'll notice it produced a bitmap for everything except for the Earth. If we look at our log to find out why, it turns out to be because this file uses Successive Approximation, which triggers these refinement blocks that we haven't yet implemented, so we get totally desynchronized in the middle of the Huffman coded bit stream. We end up reporting on encountering invalid markers, and we abort. So that is to be expected until we finish the implementation, but the rest of the bitmaps that it produced look actually perfect. There's the frog, there's the panda, and there's the parrot. So that's great, that's huge progress. Next, we'll finish the refinement implementation and see if we can get the correct bitmap for the Earth. Like we talked about at the beginning, DC refinement is very simple. All we do is we read a bit. We do our usual error checking, but assuming it's okay, we shift the bit to the left by the value of SA low, and we OR it onto the coefficient that we are refining, and then we're done. Just like that, we're ready to move on to AC refinement. As we know, this is the complicated one. Let's just start by setting the value of I to the start of selection. Now remember that if our end of band skips is non-zero, meaning we're in the middle of a skip, we need to skip the block. We don't actually just skip and return early, we still need to pass through and collect a new bit for each of the non-zero coefficients. So we have two things to do. Either skips equals 0 or it doesn't. So if skips is 0, we actually need to do Huffman decoding. So we'll start our for loop where we go up to the end of selection. This is the case where we need to do Huffman decoding, so we extract a symbol. Just like usual, we split the symbol into its upper nibble and lower nibble. Now remember, because this is refinement, the coefficient length should either be 0 or 1. It should not be larger. So first we test if it is not 0. This is where things get a little bit strange. So we know coefficient length is not 0, so we need to read a bit, and this bit will help us fill in a coefficient, but we need to hold on to this bit for a little while because we need to handle this number of zeros, as you recall from our slides towards the beginning. Additionally, since this is the first time we are getting a non-zero bit for this particular coefficient, we don't even know if it's a positive or negative number just yet. So this bit that we're about to read, that's actually what it's going to tell us. A 1 is going to mean this coefficient is positive, and a 0 is going to mean that this coefficient is negative. So the bit that we're reading isn't literally the bit that we're storing. We're not going to be storing the 0 in the case of it being 0. What we are going to be storing is a 1 bit shifted to the left by the value of SA low. So let's just put that in a variable all on its own at the start. If we take the bit 1 and we shift it to the left by the value of SA low, that is kind of the positive 1 bit. If we take a negative 1 and shift it to the left by SA low, that's the negative bit. Of course, left shifting isn't exactly defined for negative values, so to be proper, we have to cast it to unsigned, perform the left shift, and then cast it back to signed when we store it in a signed int. Then coming back down to here, we are going to read this bit now. And if it's a 1, the coefficient is that positive bit. If it's a 0, that coefficient is that negative bit, or we handle an error on the bit stream. Also, to be really thorough, let's assert that the coefficient length is exactly 1. Okay, so what if this was not the case? The coefficient length was indeed 0. Well, it might be special symbol F0, which we're going to handle separately. But if it isn't special symbol F0, then it's one of the end of band symbols, so we need to handle that now. So otherwise, if the coefficient length is 0, only if the number of zeros is not 15, if it's not special symbol F0, then this is exactly like we saw with AC first visit. 2 to the power of num zeros is the number of skips, and then we need to read another n bits, and that's how many more skips we have. Now remember, we haven't actually handled this coefficient yet. We need to go along the zigzag path, accounting for the number of zeros that we are supposed to skip, and read a bit for each non-zero coefficient along the way, and then once we're done with that, we handle this coefficient value and we place it wherever we end up along the zigzag path. So to do that, we're going to wrap this in a while loop just to ensure that we do not go beyond the end of the selection. But what matters is if the current value at position I is or is not 0. If it is not 0, we need to read a new bit for this coefficient. So to do that, we read a bit. If it is 1, we need to add this new bit to this coefficient. If it's 0, there is nothing to do. And if it's -1, we have an error. If the bit is a 1, the new bit that we're setting in the coefficient is still shifted left by the value of SA low, so we can just use our positive, negative variables that we set at the top. And which one we use depends on if this coefficient is positive or negative. So if it's positive, use the positive bit. If it's negative, use the negative bit. This safeguard here should always be true. It's just to be extra sure that the bit we are about to set isn't already set by a previous scan. Okay, next. So what if this is false? The coefficient we're looking at is 0. Then that counts as one of the coefficients that we're skipping. That's one of our 0 skips. So here we will handle that. If our number of zeros to skip has reached 0, we break from this while loop that we're in. Otherwise, we decrement num zeros by 1. Then because we're in a while loop, we do need to increment I. Now, when we leave this while loop, we are finally at the index where we handle the coefficient that we read at the beginning. So we place that now. It would be fine to simply put the coefficient into the component. This safeguard is to make sure, number one, that I has not gone beyond the end of the selection. And number 2, we only write the coefficient if it is not 0. The coefficient might be 0 if it stays its initial value and we never overwrote it here. And that would happen when the coefficient length was 0. If the coefficient length was 0 and we didn't read a bit, if we then encountered an end of band symbol, we would have broken from this for loop. But if it wasn't an end of band symbol, it was special symbol F0, and all we did was skip some 0 coefficients, then we will come down here and execute this line, so we don't perform the assignment if coefficient is still its default value of 0. Okay, so all of that was only when the number of skips, the end of band skips, was 0 and we had to do Huffman decoding. The last portion is when we do need to skip Huffman decoding and all we're doing is collecting new bits for non-zero coefficients. This is going to look a lot like this do while loop here. If we find coefficients that are not 0, we read a bit, and if the coefficient is positive, we add on the positive bit, otherwise we add on the negative bit. So let's add that here. So if skips is positive, no Huffman decoding, but we still go to the end of the selection for this block. If the coefficient is non-zero, we read a bit. If that coefficient is positive, we add the positive bit, otherwise the negative bit. If the bit that we read was 0, we do nothing. And if the coefficient we're looking at is 0, we also do nothing. Then once we are done with the selection, we decrement the number of skips. We have handled a block that was skipped. I appreciate that that can be a lot of information at one time. It certainly was for me. So don't worry if you want to re-watch that section a couple of times to really get your head around it. Now let's see if we can produce the bitmap for earth.jpg. And it did produce a file. Let's see if it looks correct. And there we go. So now we're handling all of progressive decoding, both spectral selection and successive approximation. However, we're not quite done. Let's make yet another subfolder for some new tests. And these tests are going to be both progressive and subsampled. We have a picture of a penguin, a sloth, and a tiger. Let's try converting these images and see what we get. Well, we got a file for penguin and sloth, but not for tiger at all. And here's what penguin looks like. Interesting. And here is what sloth looks like. Very interesting. So what's happening is, like I mentioned towards the beginning, subsampling and the ordering of blocks gets reevaluated based on which components are present in the scan. And we have not accounted for that yet. So we were able to decode the bit streams just fine, but we placed the coefficients in the wrong spots in the overall image. In the case of sloth, it appears that all the chrominance data is correct, but the luminance data has been split in two and is alternating from the left and right side of the image. And with a penguin, it looks like the same thing has happened, but it's actually easier to tell. Chrominance data is correct, but luminance data, the brightness information about where the hard edges are, has been split. So why then is the visual corruption of sloth and penguin not exactly the same? In sloth, we see two whole copies of the sloth's face, and we can see all the details of the hairs on its head. But the penguin only has one colored body and none of the fine detail. Well, it has to do with how scans that include all three color components use subsampling in the same way as before, and we definitely handle that correctly. The only scans we won't handle correctly are luminance-only scans, which may be DC or may be AC. In the case of penguin, the DC scans included all three components at once, so we handled that fine, and over the entire image we have the correct average color and average brightness for each block. It was only the AC scans that threw us off, and the AC scans give you hard edge details. Whereas for the sloth, even for the DC, the luminance had a scan all to itself, so we interpreted that scan incorrectly. For the luminance, both the DC and AC values are being split like this. So, how do we fix it? Well, where do we handle the placement of subsampled blocks? That is here in Decode Huffman Data, where we use the sampling factor to determine how much we advance by on this YX loop, and we use the component sampling factor to decide the maximum values of V and H. So if we encounter a scan that mixes luminance and chrominance data, we don't want to change anything. We want it to work the same way as before and handle subsampling accordingly. However, for scans that are only luminance, we basically want to ignore subsampling. We want to decode blocks and then place them in the image straight along each row. So let's ask that question. Is this scan a luminance-only scan or not? We can ask it like that. If the number of components in the scan is 1 and component 0, the luminance, is in the scan, then this is a luminance-only scan. Now, this y plus and x plus here, where we advance by the maximum sampling factors, instead of using the maximum sampling factors, let's use a new local variable called y step and x step. And the value of these variables might be the maximum sampling factors, but if it's a luminance-only scan, the values of x step and y step will be 1. So we can use y step right here and x step right here. Okay, next, let's do basically the exact same thing on the v and h loop. Make two more local variables called vmax and hmax. And they will be equal to the component's sampling factors a lot of the time, but if it's luminance only, they will be equal to 1. Then here we can use the value of vmax. And here we can use the value of hmax. And there we go. Now let's see if we can get the correct output for penguin and sloth, and let's see if we can get any output at all for tiger. So there we go. Now penguin looks correct, sloth looks correct, and tiger also looks correct. The last thing to show is that the calculation of this restart interval variable also needs to be affected by luminance-only scans. So we'll do that here. We'll move that variable down. And now it basically just uses x step and y step instead of the maximum sampling factors like it did before. So there we go. All that craziness just to handle progressive JPEGs. I don't know about you, but I'm exhausted. Hopefully you enjoyed that journey. Hopefully it made sense. If not, leave your comments below and I'll try to answer your questions and provide any clarification where I can. Other than that, I thank you for watching. And when we come back, we will turn this all around, take everything we've learned, and make an encoder that'll take pixel arrays and create JPEG files with their own Huffman coded bit streams. Thanks again, and I'll see you then in episode 10.